The shaft in the figure consists of a 3-inch diameter aluminum segment that is rigidly joined to a 2-inch diameter steel segment, and the ends of the shaft are attached to rigid supports. Calculate the maximum shear stress developed in each segment when the torque T is equal to 10 kip-inch is applied. Use G is equal to 4 times 10 to the power of 6 psi for aluminum and G of 12 times 10 to the power of 6 psi for steel. So if you can notice, you can observe immediately that example number 2 is quite the same illustration for problems under statical indeterminate in our analysis of strain. So that is something that we can expect already. Okay, so first we write our given, which is diameter of 3 inches for our aluminum and 2 inches for our steel segments. Next also is the value of our torque, which is 10,000 pound-inch or 10 kip-inch, and our G's for our aluminum and our steel. Four times 10 to the power of 6 psi for our aluminum, and 12 times 10 to the power of 6 for our psi. For our steel, sorry. 12 times 10 to the power of 6 psi for our steel. Now, since this problem is statically indeterminate, so therefore we will be looking into the relationship between one material for rather the relationship between the performance or the how our material moved, how our aluminum moved in response to the movement of our steel. Okay, so like just what we did in our analysis of strain. Now, what is required for this problem? We are to solve for the maximum shear stress for each segment. Okay, we write our solution. Okay, it is always best that we incorporate in our solution some free body diagrams or some sketches, because it really helps. It really helps. It makes us understand the problem more. Okay, so what we are doing now is we're trying as if we removed our aluminum and our steel from the fixed supports, both left and right. Okay, now there is torque at the middle, right? There is torque in the middle, so therefore if we join two materials, aluminum and steel, and then we twist them at the middle, at the point where we connect them, you would notice that both of the material will simultaneously rotate as well. Okay, but before we dive into deriving our compatibility, let's do first equilibrium equation, which is summation of moment along x direction. And if you can notice, Both our torque for aluminum and steel did not follow the natural curl of our hand, so therefore T aluminum and torque steel is negative, while the given torque, which is 10 times 10 to the power of 3, is positive. Okay, so that would be our first equation, which is our equilibrium equation. Next, we derive now our compatibility. And just like what I said, if you can notice, if you try to rotate, if you try to rotate our aluminum and our steel at the point where we joined them, both aluminum and steel will simultaneously rotate as well. And if you try to recall your dynamics of rigid bodies, especially with angular with rotation, although steel has a much smaller radius as compared to aluminum, but nevertheless both of them, if you say you rotate them together simultaneously, they will the angle of rotation for both aluminum and steel will be the same. So that is why our compatibility equation is angle of twist of aluminum is equal to the angle of twist of our steel, wherein theta, which is our angle of twist, is equal to TL over JG. Now we substitute. TAL, which is the torque, is unknown. And then the length of aluminum is 6. So we multiply that by 12 to convert that into inches. And then our J, which is pi over 32 d to the fourth power, which is for aluminum, that's pi over 32 times 3 to the fourth power times the shear modulus, which is 4 times 10 to the power of 6, and it is all in psi now. Now on the other hand, for our ST, the length is 3 feet, so times 12 again, and then the diameter is 2 inches, so that's pi over 32 times 2 to the fourth power times 12 times 10 to the power of 6. Now we will try to solve. You can always have it in terms of AL, or you can have it in terms of ST. For my case, since AL is already in the left hand side of the equation, so I solve it in terms of AL. I solve AL first in terms of ST rather. Okay, so we have T sub ST times 3 times 12. Let me just transfer that. Okay. Multiplied that by the denominator of the left hand side, which is pi over 32 times 3 to the fourth power, quantity close times 4 times 10 to the power of 6. All over the denominator on the right, multiplied by the numerator on the left. That is pi over 32 times 2 to the fourth power times 12 times 10 to the power of 6 multiplied by 6 times 12. Now we can input everything in our calculator. So I'd like to refer you guys to the calculator on the left. Times 12 times 10 to the power of 6 times 6 times 12. So the resulting answer would be 0.84375, and of course you bring down T sub ST. And that is our equation number 2. What we will be doing next is substituting 2 into 1. So let me just copy. That's 10 times 10 to the power of 3 minus TAL minus TST is equal to 0. And bring all of that at the bottom. Okay, so basically I transferred TAL and TST in the other side of the equation, the other side of the equal sign. Then substituting TAL is equal to 10 times 10 to the power of 3 divided by 1.84375. So TST is equal to is equal to 11,851. I'm sorry. It should be 5423.728.813.559.32. Well, the previous answer, it's because I did not add 1, right? I forgot to add 1. So just make some corrections. So the final answer now for our T sub ST, the torque at ST, is 5,423.728.813.559.32 pound-inch. Now we are to substitute T sub ST into equation number 2. So let me just copy that. And then substitute the value. Okay, so the torque at AL is 4,576.271,186,44068 pound-inch. However, we are asked to solve for the maximum shear. Okay? Okay, for the aluminum, shear stress is equal to TR over J. And for aluminum, the torque is 4,576.27118644,068. And the radius is 1.5 inches. Divided by pi over 32 multiplied by 3 inches to the fourth. So the shear stress in our aluminum is 863.21325066791, and that is in PSI. Okay, don't forget to box your final answer. Now you might be wondering, how is it that the for TR over J, the final unit is in pound per square inch? Now take note that torque is in pound inch and then R is in inches, so it becomes pound inches squared. Now for J, your J is raised to the fourth. So the answer for our J is inches to the fourth power. So if you have inches squared in the in the numerator and inches to the fourth in our denominator, then the resulting unit would be 1 over inches squared. So the numerator has a unit of pound, so that is pound per square inch, or PSI. Now for our steel, it just follows what we did for our aluminum. So that's TR over J. The torque in our steel is 5,423.72881,355,932 multiplied by the radius 1 inch, because the diameter is 2 inches, divided by pi over 32 multiplied by the diameter raised to the fourth power. So the resulting answer is 3,452.853,002,671,63 PSI.